good morning or good evening to all, and welcome to the Data-Driven Community virtual meeting. My name is Ronen Arvedi. I'm from Israel, working as a senior consultant. I'm co-admin of the Data-Driven Community. I'm honored to be moderator today on this session. A few words about the Data-Driven Community. We are managing two branches of activity. One is an annual conference called Future Data Driven Summit. We will start to plan the Future Data Driven Summit 2024, probably in about few months. We just finished the last conference in September. And the second activity is the weekly meeting of the Cloud Data Driven User Group, like today. During the meeting today, please use the chat for questions and discussion. With that said, the meeting today is a bit shorter than usual, probably. So if we will not be able to answer all the questions, then we will try to publish the answers after the meeting. Please remember, this is a user group meeting. It's not a conference. So we are flexible with the time. Feel free to discuss in the chat. You can answer other people's questions as well. You are also welcome to use reactions. It doesn't interfere the course of the meeting. If you hear something that you love, like, or you want to clap your hands, then feel free to do so with the virtual reactions. I love it a lot. Today we are hosting Güldeniz, and probably you see this complex name. I have no idea how to pronounce the full name. In fact, it includes characters which I don't even have in the keyboard. So I will let Güldeniz to present herself and the full name better than I can. So Güldeniz, you're welcome to share your screen and take control. I will follow the chat, and if there are questions, I will pass the questions to you. Okay? And start yourself.
Okay. Thank you, Ronen. I'm going to share my screen right now. Okay, you should see my screen, right? Okay, great. Hi, everyone. Today we're going to talk about text-to-image models, which this topic actually is so popular in this time, you know, like OpenAI, DALL-E, and OpenAI, like what OpenAI does right now. This topic came to our life very newly, and everyone knows text-to-image models only for DALL-E. You all know DALL-E, like DALL-E generates images by prompts and really generate great images by prompts. And this was a really, really big thing in this artificial intelligence industry. So, but people know text-to-image models as DALL-E, but actually there are more text-to-image models. And in this presentation, I'm not going to bore you because this topic is just kind of a generative AI topic, and this kind of topics might be so complex in itself. So I won't bore you with all the details and all the technical stuff because I don't know them too. But I just want to show you some other models like DALL-E. Imagine party models like Google made. So in this session, we're just going to talk about what text-to-image models and how people make text-to-image models, like how they produce images by prompts. I'm going to just walk you through that. And if you would have any question, you can just ask me. And like he said, like we can just argue your questions. It's open presentation. And let's begin. So I think you can see my, I'm going to just introduce myself first. My name is Güldeniz. I know my name has some different letters, but you can just call me Deniz. It's easier.
I must understand how to pronounce it.
Okay. Güldeniz is hard to pronounce, really hard to pronounce. I know that. So I knew that. So I was going to mention this in this presentation. But Ron asked me before that. So I just remember that I should have mentioned that before because my name is hard to pronounce. So just call me Deniz. It's easier. And I use this name actually normally in my life. So I work as an AI engineer at TürkNet, which TürkNet is a really like one of the biggest internet provider company in Turkey, like Turkey. And I have a workshop series in Turkey actually. One of them maybe the first and more advanced physical workshop series called More Than 101. And I helped so many people through this workshop series. Like we were doing advanced artificial intelligence workshops. So we were just giving people some practice about this data industry for their future job opportunities. So these are my contact info. You can just contact me anytime you want. I use Twitter mostly for technical stuff, and I use Instagram just like technical stuff. And you can email me if you have any question about this presentation or anything about other things in this artificial intelligence stuff. You can just mail me here. And you can see these images. One day, we all opened Twitter. Like I assume you all use Twitter. And even though if you only use Instagram, we're going to talk about that too, because you saw these images on Instagram too, not only Twitter. And we started to see these many pictures, pictures that looked very realistic, but at the same time, were not real. Look at this dog, it looks really, really, really realistic. But you know that something's not real. You know, it looks really good. And this avocado chair is just like so famous, if you know that, because it was one of the first pictures DALL-E produced and they shared. So those pictures are so great. It was an innovation that reached out to everyone, whether technical or non-technical. That's why everyone was talking a lot about the subject. Because like I said, you didn't see those images only on Twitter. You saw these images on Instagram too. On the other hand, DALL-E's developer, we all know them, OpenAI, had developed such a different advertising strategy that they opened an account for the model on the Instagram too. They asked for prompts from people and gave these prompts to DALL-E and shared their output. By doing this, they attracted the attention of people from every platform. After all, there was no paper or code implementation. People only saw the results. In this way, artificial intelligence started to be talked about more and more by everyone. Because usually this kind of technological breakthroughs will only be seen by AI researchers or data scientists or big companies or researcher companies. They will just read the paper, maybe implement the code, or if the researcher group had made a Hugging Face spaces, they can just try the model there. But that would be inside this little artificial intelligence groups. But they really took this so far. They aimed the world. They created this AI user thing. People were calling themselves now AI user just because they use GPT's API or DALL-E's API. So OpenAI went for the world. So they made people more know about artificial intelligence. People always scared of artificial intelligence, but now they see DALL-E and they scared even more. Okay, let's examine some examples. If we examine a few examples, you may think that this picture is straight out of a game or a movie. You only see this kind of a like picture, like image, only on a game or a really sci-fi movies, right? This looks very realistic, very good. And we can observe that as the detail in the given prompts increases, the details in the generated image increase too. If you look carefully at the image in the left side of the screen, you can see many wrong things. Actually, it's like you look at the pool. It's not even a pool. It looks like a beach. It looks like a beach, and then the water is coming down to couch. It has to be actually a pool, like in the prompt set. But we can say that it is a good step to reflect so much details, because we create a model and we want this model to generate images by prompts. So it's actually wanting so many things from something, like from a baby. Like you want so many things from a baby, like it doesn't even know yet, but you want to teach it so it will grow and make you really like really good right images for your prompt. So this result actually not that bad. And then many models and spaces have been created on Hugging Face. I hope you heard about Hugging Face before, but at the end of this presentation, I'm going to talk about Hugging Face because they have a really good library that you can use this state-of-the-art text-to-image models actually. At first, DALL-E was not open to everyone, as I remember. That's why they opened Instagram and they wanted prompt from people, and they generated in DALL-E and then shared outputs. And as far as I remember, it was paid after a while. That's why open source DALL-E Mini was created, and I know that DALL-E Mini was not that good. Like the earlier pictures that I shared with you, and the DALL-E Mini's generated images were not the same, because there's not the same DALL-E actually, and people went around with DALL-E. They were all like, people were talking about DALL-E, like DALL-E is so great. Wow, OpenAI, what are they doing? But actually, there's a good question, like how do they do that? How models generate images from prompts? I think this is a really, really big question, because normally we're so, I don't know if you work as a data scientist or you just wants to start with data science or artificial intelligence, but it's easy to, maybe classify an image as a dog or a not dog, or I don't know, to predict a house price by its features. It's easy, but you want a model to generate a picture, like a really realistic picture. Like every pixel, they wanted them to create it and then make it a really, really meaningful thing for a human eye. And it's not an easy thing to do. So how do they do that? They do that with deep generative models. As I mentioned at the beginning of the presentation, DALL-E was not the first of its kind. In fact, text-to-image models have continued to be developed for years with the model architecture it adopts. Yes, DALL-E may be the biggest model that has produced the best results so far, but although the first version and the last version adopt different architectures, the basis they follow, like the fundamental idea of model, is the same. We call this deep generative models. Deep generative models learn the distribution. Learn the distribution of X within itself without Y. This is unsupervised learning. Instead of adopting the logic that we are accustomed to, X directs us to Y, which is supervised learning. Generative models, which are examples of unsupervised learning, are the most popular models. It forms the basic logic of most famous models that I will talk about shortly. With generative models, instead of learning the relationship between X and I, we'll learn the distribution of X within itself and tell the model to produce something new in accordance with the distribution. Because at first, people think that when you just create a text-to-image model, they think it will generate an image, just will look like on its training data. It's actually not happening like that. This is the thing, actually. It learns the distribution of its training data. If you give them like maybe 1,000 images of my face, yeah, it will produce faces by the distribution of my face, because it learned my face's distribution. So its reality will be all about my face. So it will produce face like me. Maybe you won't be able to even produce picture of myself. So generative models really adopts a really different way of learning, and which is a really hard to train. It requires a lot of data, a lot of computational power. They adopt different mathematical concepts in it. Like we're going to talk about diffusion model, but diffusion model adopts thermodynamical. I think it was about thermodynamics. They adopt thermodynamics rules, actually. It has something like complex stuff. So it's actually mind-blowing, and it's, I think, perfect. And that's why we're going to go through the 4 best examples of generative models. So these 4 models are the most famous and successful generative models. Generative adversarial networks actually are very, very precious to me, because I first started my generative AI. It wasn't, the generative AI wasn't even a thing back then, but I started learning all those image generation stuff with GANs, so they're really precious to me. So let me talk about generative adversarial models, and which you might not hear this model type lately, because people are mostly talk about diffusion models. So GANs kind of like got forgotten, but they did something else. I don't know. It was maybe it was like 3, maybe 6 months ago. They made a really, really great paper. People were talking about like GANs are back. There were like tweets like that. So GANs are kind of gotten forgotten, but they are the really, really one of the biggest and first models in text-to-image models, deep generative models, actually. So this model includes 2 architecture. One is a generator, and the other is a discriminator. Okay, while the generator generates images, the discriminator predicts whether these images are real or fake. So while the generator tries to make what it generates so realistic that the discriminator cannot understand it, the discriminator tries to improve itself enough to understand the generator. So it wants to know that, it wants to label all the images that generator generated as fake, because it's fake. But generators try to make it so real that discriminator wouldn't even understand. This architecture is a very interesting one, because we can say that the 2 architectures are in competition with each other. This was one of the most exciting architectures to come out in a long time. Of course, it has certain disadvantages, such as needing of a lot of data. One model improving much faster than the other, because a discriminator's job is pretty easy. It only has to learn to label an image as fake or real. So at first, generators generated images are so bad that it knows that they are fake. So discriminator's learning process is kind of going faster than generator, because generator's job is another topic. Generator just trying to generate new image, very, very good new images. So this is kind of a problem. So there are some optimization stuff going around in GANs, and they have all their like versatile generative adversarial networks, like they have their own papers, and it needs much more data, because you just want a model to produce new and realistic images. So you probably will need a lot of data, and that's why image computer vision world is kind of much more slower than NLP, because image data sets are not easy to find, and we need as much as images for to generate new images. And another model is variational autoencoders. And this model includes two structures, like actual generative adversarial networks, encoder and decoder. While decoder shrinks the input, the decoder tries to return this shrinked compressed image to its original state. DALL-E also used this architecture and two transformers as its basis. Later, it transitioned to a more successful and popular structure. In fact, you can see it at the bottom of the screen right now, which is diffusion models. But at first, DALL-E used variational autoencoders, and then it switched to diffusion models after they stated that diffusion models might beat the GANs generating images. So what you see right now is a history of text-to-image models, because like I said at the beginning of the presentation, DALL-E is not the first of its kind. There were more tries of researchers made, but it's not going really back, because it's the first work made in late of 2015. So we're going to just walk through this history line, and we're going to come up with our latest technology and models. Okay, the idea of synthesizing or generating an image given a caption began with the early work of Align Draw. Like I said, GANs and variational autoencoders, they generate images, but they don't take prompts. Prompting is real, like kind of new thing. Like you see, they started to work on it, like work to get generated images by a prompt in late of 2015. So this is a kind of new thing, and this is began with early work Align Draw. However, the image quality was very low, like as you can see here. This is not because of this image quality, it's because this image quality is really bad. And the scenes and the objects generated were barely recognizable. This was followed by 5 years of, as you can see here, models improvements instigated by the progresses of GANs. And people were working on GANs. You know, GAN was kind of one of the best model back then about text image models. So people were working with GANs, as you can see, with models such as ATT and GAN. I think you can just read it as attention GAN. I'm not sure. I remember attention GAN might be true, and DM GAN and or DF GAN. Although some of the content of the captions was beginning to be represented, the images were still not realistic, except for restricted and simple datasets. For example, the cube dataset, which only consists of bird images. And integrating learning in the pipeline, and especially increasing the dataset size, like I just said before, that it was the model before DALL-E was working fine with really restricted and little images, only one labeled images. But now they increased the dataset size and enabled XMC GAN to produce better images, depicting clearer scenes. In the same vein, authors of DALL-E showed that further scaling of the dataset to 250 million image text pairs could enable zero-shot learning. Thus, the DALL-E model is able to mix different objects, concepts, and places to produce non-iconic images. For example, avocado chair. I just show you in the beginning of the presentation. DALL-E, however, doesn't use GANs and instead exploits the VQ variational autoencoders, as well as two transformers of the transformer model. And although DALL-E 1 outputs were seen as astonishing, a novel category of generative models demonstrated that it was only the beginning. And the same year, like you can see this 2021 and 2022 was crazy about image models. And the same year of the release of DALL-E paper, Darewal and Nicole showed that diffusion models could surpass GANs on class conditional image generation. As you can see, it's somewhere here, because after that Glide came up. Then Glide introduced diffusion models for text-to-image synthesis generation and obtained higher quality images than DALL-E. So it showed that diffusion models was way better than DALL-E because they both trained on the same data set. DALL-E and Glide trained on the same data set. Only thing was different, the model. Glide used the diffusion models, DALL-E used variational encoder models. So you can just understand this is a really big difference. The authors of Glide, and as I remember, I think the authors of Glide was also a researcher of OpenAI, and I don't know, but I remember something like that. The authors of Glide use a transformer language model to embed the textual image descriptions, and then diffusion models conditioned on the embeddings to produce images. Again, actually, there are two architectures. One is embed the text, and the second is creating the picture out of that embedding. But then, during the development of this thesis, two major works were released a month apart, DALL-E 2 and Imagine. Imagine is by Google, and as I remember, after like 2 weeks after Imagine published, after like DALL-E 2 published, as I remember, 2 weeks apart, two big model came up. DALL-E 2 is very different to its former version, and similarly to Glide, it decodes embeddings to generate images. However, the embeddings come from CLIP. CLIP is a model of OpenAI, a vision language model learning image text representations. And so to keep it short, two CLIP encoders produce embeddings for images and texts respectively. So they embed image and text, and then they come up with the embeddings, and then a diffusion model produce the image. DALL-E 2 leverages these pre-trained encoders and learns a prior model to translate from a CLIP text embedding to a CLIP image embedding. Imagine, on the other hand, is more similar to Glide, but instead of training from scratch the language model, embedding model actually, the authors reuse a large frozen transformer model trained on a massive text-only corpus called a T5 model. And then they exhibit that increasing the size of the language model leads to higher improvements than increasing the size of the diffusion model. Besides, they double the size of the captioned images dataset and propose a few tricks to generate more. And they say Imagine was like kind of better than DALL-E 2. So it's kind of really hard to process, I know, and those are maybe not that important to know, but I think it's kind of important because, like I said, DALL-E is not one of its kind. So knowing about Glide and Imagine will keep you on track, and you will more know about what's coming or what is happening in this industry. So we talked about something a model made DALL-E better. Diffusion models. What are those diffusion models like? What kind of structure does a diffusion model follow? Diffusion models add noise to the image and then apply denoise, returning the image to its original state. Actually, it's so easy. It looks so easy, actually. It looks pretty easy. It just, like I described it here, it we're training a model to learn how to denoise to get back to the original image. This is basic. So model adds noise to the image until, like, little by little add noise to image, and then after all you can see is the noise. It just denoise it to get back to the original image. Actually, this is all diffusion model does, and this model architecture works really, really fine, even better than GANs and variational twin encoders. So that is switch to diffusion model because it's better. And we saw that a glide with diffusion model and DALI with variational twin encoders were not the same, even though they train on the same data set. And it's really, really big data set. So in a way, we can say that it resembles the structure of variational twin encoders. After first change is changing the input structure of the input, and then we try to restore it by decoder. It's like kind of like, you know, it's always sound the same like in GAN. GAN was pretty different actually, but it has to be always two architecture working against each other or just working together. Like in GANs, they were generator and discriminator. They were both working with each other to get better than the other one. In variational encoders, we were trying to break the input, like shrink the input, and then we're just trying to get it back to its original state by another model. In diffusion model, we do the same. Like we add noise to the image, and then we just denoise it to get the original image. So then we wanted to produce image from noise by embedding text. So let's add this embedding, because we just talked about that diffusion model, only image part. It adds noise to image and then denoise it to get the original image. So let's add a text to it. So imagine adding text into this process. As I just mentioned, you have text and image pairs, like a golden lap puppy, tongue hanging out and wearing a blue collar. This dog image. In the imagine, like we're going to go with imagine. In the imagine model, the frozen embedding model, like T5, separates the text into embeddings, and then our diffusion model generates the image according to this embedding from a noise. So our model was already trained to learn this process, the noise and image to its original state by embedding. So we just give it a text, and then text encoder separated it, converted to embeddings, and then we just generate image from a noise by these embeddings. To wrap it up, I just actually sum it up everything just now, but let's say it again. To sum everything up, an embedding model separates the text into its embeddings, and on the other hand, the diffusion model learns to turn an image consisting of noise into an image suitable for that embedding. Okay, so the last part in this presentation, I think I just want to add this part because I really, really love the idea, the Google made. And like I said, I don't want you all to know the DALI model. I want you to know more models like DALI, maybe better than DALI, because there are really good models out there other than DALI. So this is one of them. Then this is made by Google, and I really find it very like great idea. And you know that in a natural language processing world, they, like I said before, they move pretty fast, and then we adopt things from them. Like we adopt vision transformers from transformer NLP. You know, when transformers came up, like people went crazy because transformers were great. And then someone said that, why don't we do that for computer vision? Like, why don't we use that on image? And then they came up with vision transformers, seven transformers. It was great. Transformers were great for image data sets too. So in here, Google actually made the same thing. they use autoregressive approach. And this model is called party. The logic used here is what we are used from sequence to sequence models, actually. The sequence to sequence model maps one text to another text, like translation, maps one language to another language, like Turkish to French, French to Turkish. This is sequence to sequence model. And the following question was asked here. Can we map a text to the tokens of an image? This is great. This is a great idea. So they think that let's give it a sequence of text, and then we get tokens of an image. So basically, we want model to predict image tokens of a text, and then reassemble those tokens into an image. So this is what party does. Like you can see in this examples, like a hockey game between a blue and a white team, and you can just, it's kind of really tiny here, but you can see there are tokens, and then they reassemble it into an image in the middle. I think it's a really great idea. The things they, the way they follow, I think this is kind of great. I love this kind of idea, so I just want to add it here. So I wanted to all know that about party. So it's a great idea. This is a great another model, and then I am done with the presentation. So after this, I want to show you diffusers. So diffusers is like it said here. It's a go-to library for diffusion models. Like if you want to learn more about diffusion models, and like I said, this kind of generative AI models, like in large language models or in a text-to-image, diffusion models or GANs or variation encoders, they are not easy to train on local computers. And if you have enough budget to use cloud, you can use cloud like AWS or Google Cloud, but you cannot just train a really good model on Google Colab or Kaggle or on your like local Jupyter notebook or Python file. So our best thing to do, the best thing we can do is to use them through some libraries. And they are like more than enough for your work. You can just use them on your apps, or you can just try them and understand them more, because they have a really crazy good documentation, as you can see here. So I thought that everyone knew about diffusers, but before I talk about in my other presentation, I heard people didn't know about diffusers. So I just wanted to mention diffusers in here, because we talked about diffusion models and other state-of-the-art pre-trained diffusion model includes stable diffusion models. So you might want to check out this site. And there are they have a GitHub repo as well. This is what I love Hugging Face actually. So they have notebooks. I think this, which is great. And like custom diffusion, you can come here and there are codes how you can. Let's do text to image, and there are like LoRa flags. There are a lot of Python files, or there are some dogs. There are a lot of good stuff in here. So I just would like you to check it out.
Something other than the slides, then we cannot see it.
Oh my God, why? Oh, I'm so sorry. Let me show them again. Okay. Oh, I'm so sorry. I thought you saw that. Okay, now you can see, right, a GitHub repo.
Yes, now we can see the GitHub. That's okay.
Okay. Diffusers is a really great like library, as I said, and what I love about Hugging Face, like I said before, it's GitHub repos, because they have really detailed GitHub repos. So please check it out. So not many people heard about diffusers before, and it's really confusing for me because I thought everyone knew about diffusers. But I think the theory is kind of hard, but implementation part is they made it easier. You know, you can just always check it out and contribute to this great GitHub repo. So I'm just trying to see if there's something that I can show you real quick. Oh, here, like this even quick start, you can just, all you have to do to import the diffusion model, and then you can just try any diffusion model you want, like in diffusers. Like I said, training them on your notebooks or cloud, it's not cost effective. So you might just try it on diffusers library. It's a really great source, and I will love to see your work actually. So this is kind of my recommendation to you after this, because we talk about like DALL-E is so great, and all we do to just give prompts to DALL-E and then okay, done, like our job is done. I don't like that. So I would like to learn, like know more and control more about those state-of-the-art diffusion models. So this kind of notebooks and libraries are really, really great way to start to get a practice of it, because you can use it even in your professional life or in your personal life project. So thank you, everyone. Thank you for listening. I hope that you find it very instructive. It was kind of a short presentation, but like I said, I didn't want to bore you. I just want to give you the enough information about text-to-image models. And I'd like to do more. I'd like to do more practice and code implementation workshop too in the future, maybe. Who knows? So so glad that you listened, and I hope you understand it. And this is my first live English presentation, so I hope I didn't do anything wrong.
Before you show your last slide, if I may, since we do have time, I want to mention a few. First of all this session was basically about Dell, mostly, and in the timeline, there is something that's missing, which is a new option. If you are lazy, mostly, and you don't want to train it yourself, Microsoft have something that's called Microsoft Designer. It was just released a few weeks ago. So it's really good tool in order to produce images. And to mention one more important thing is that don't expect to get a result of real images with minutes. It can be a lot of work. There are a lot of issues with creating real images, try to make it look like real, which allow actually detection of fake images. I do it a lot, not the fake images, but detection of fake images online. I can present you just some point, for example, that you can notice when you are looking on images on the network. You might find a lot of cases that the shadow, for example, of different objects is in a different direction. This happened, or you can find people that have a different number of fingers. It's very common to get an image of a person that have 6 or 7 fingers, or missing a face feature. None of the AI at this time does not succeed to do it perfectly, and there are a lot of cases. Most of the cases you will find that our face are too smooth. They are basically too beautiful, too symmetric. So think about this when you create something, or when you want to find something fake. There are a lot of other points which I will not take your time now to speak about it. One more point, the last point, is regarding creating avatar. It's related to what I said before. I have tried to create an avatar of myself. Now, I want the avatar to be avatar, not a real picture. but I wanted to look like myself. As you can see, I don't have hair here, and I couldn't. I mean, I can if I will put more hours of work on this. The avatar by default that all the tools today create are too pretty. You can create someone with full hair or without hair, but it's very difficult. Until now, I don't know which code to use in order to get someone that has short hair with missing hair in the side. So just take it into consideration. It's not always something that you do in minutes. It can be hours in order to present a good image.
Yeah, it took hours, and sometimes it took hours, and then the thing you see as generated is kind of trash, it doesn't something that you want. It could be better. So it's just really, really not easy thing to do. And I hope you made
slide to show. You start to say it, and then I present mine. So you can show your screen again if you want.
Mm-hmm. I hope you all understood me very well. Like I said before, this is my first English live presentation. I did that before, but it wasn't live. So I hope I made myself clear and you understood most of the thing I said. So thank you.
It was a great session. Don't worry, you can continue speaking in English. So I want to thank you. I want to thank the speaker, Denise. If there are more questions, you can use the chat now. You can open your camera if you want to show your face. The option is open for everyone now. And I want to thank all of you, everyone that joined us today. I highly recommend to follow us on social media to get updates, information, and don't forget to check the community website. I gave you the link on the chat. There you can find the list of upcoming events, the user group, and the other events that we are managing. And you are welcome to open the camera if you want before we close the meeting today. I see a lot of thank you for the speaker in the chat. I didn't miss anything. I don't see a question. So, yeah, I agree. Outstanding presentation. Thank you, Denise.
Thank you. Thank you. Thanks so much. Nice to meet you.
Great to meet you. Okay, we will close the session in about a minute if there are no questions. And thanks again for joining us, everyone.
Thank you. Oh. You can contact me anytime you want. I just shared my contact info. You can just contact me about anything. Thank you again.
After the meeting, I will contact you, or Jen will contact you regarding the presentation if you want to share. So we will collect it and pass it to the community. And we do record this session. Hopefully it will be okay. We never know how it will be recorded, but usually it's working great. So we will share the recording. You can see Jen Joseph in the chat. He joined to us. Jen is the founder of the community. You can follow us on Twitter, LinkedIn, whatever you want. Usually both of us publish the recording, the link to the recording when it's ready. So just find us on social media.